Alright friends, welcome back. In this video I'd like to go ahead and cover section 2.4 of your textbook, and the title of it says we're going to start to create a library of parent functions, but primarily in this video we're going to be talking about linear functions specifically, okay? So just a little bit of something that you guys were first introduced to in Algebra 2. This concept of a parent function is that we have all these different function families, right? We have your linear functions, we have your quadratic functions, your cubics, you have other types like your square roots, your absolute values, okay? What we like to think about, since we have so many different variations of an absolute value function or so many different variations of a cubic function, is we like to kind of consider all of the cubic functions that you could possibly graph into a family, okay? And we like to kind of think about that family as having a quote-unquote parent, which is basically the most basic example of a function of that type. Okay, and so here in the example of your constant functions, right? So this is just a function family where your output is just equal to a single constant, some number, right? So as an example of that, you might have a function that looks like f of x is equal to the number 2. This would be the machine where if you turn it on and you feed it an input, it's just always going to hand you back a 2 no matter what you gave it, okay? Well, we like to kind of consider the parent function to be f of x is equal to just some number c here, because then whenever we start altering values of c, we're going to get a whole bunch of different variations of this parent function to create all the different functions that live in this family. So that's why we kind of refer to it as a parent, is because all of the different constant functions begin with this simple function right here. And the idea is the same no matter what type of function we take a look at. So here, this is called your identity function. This is your parent function for your linear family, okay? So for your linear family of functions, we know that in general, those functions tend to look like f of x is equal to mx plus b, but this would be an example of that, because if you just have x, that's just the example where playing the role of m is 1 and playing the role of b is 0. So that's what I mean by the most basic version, or the most basic example of a function of this type. It's by changing these values of m and b that we get all the different variations of this parent function in that family, and so that's why we refer to that as the parent. For your quadratic function family, the most basic one here is just simply f of x is equal to x squared. In general, you would have other different forms that you could write all the quadratics with, but it's by taking a look at the parent function here and by altering the look and feel of it that you get all these different variations of your quadratics. Same thing with cubics. Your parent function, your most basic one, is your f of x is equal to x to the third, and you have all these other ones here, like your square root family of functions. That's the most basic version of that function. For that family, you have your reciprocal functions, so 1 over your input. If you start changing what that function formula looks like, you're going to be changing what the graph looks like here. And then the last one that I really want to call your attention to is your absolute value function. So this is definitely one that you've seen for a long time. And again, the most basic version of an absolute value function is just straight up the absolute value of your input. Okay, so this is what we mean by a library of parent functions. These are the most basic functions of these types, and it's by changing the function formula of these parent functions that we get all the different variations from these families. But specifically for the rest of this video today, I want to specifically hone in on just your linear functions and talk about how we would go ahead and analyze those and that kind of thing. So what we said before is that whenever we start to take a look at the wider family of linears, then all of them fit this form right here, where your function output is equal to some m times x and then plus b. We're going to do our analysis based on the exact same stuff that you guys learned about in Algebra 1 here, where you learned that m is the rate at which your linear function is changing, or in other words, that's the slope or the steepness of your line, and b, that is where your function crosses the y-axis, so we would call that the y-intercept, of course. And just don't forget that that point actually has coordinates, right? So that would be an x-coordinate of 0, and then the y-coordinate would be whatever the number b actually is. Okay, and so what we can start to do is start to toss you questions that look like this, where it says write a linear function. Lost my place there. There we go. Write a linear function for which f of the input of 1 is equal to an output of 3, and f of an input of 4 is equal to an output of 0. Okay. Well, really, this is the type of question that you've answered before, but maybe not necessarily in the context of functions, because what I've given you here is definitely something that looks like f of your input is equal to your output. Okay, so we've turned the f machine on, we fed it a 1, and it spat back out a 3. Okay, well, remember that ordered pairs, whenever we plot them, that goes x-coordinate, y-coordinate, and your input is your x-coordinate, and your output is your y-coordinate. So whenever we give you this information written in this way, what we're really trying to convey is the fact that you guys have an ordered pair here that looks like an x-coordinate of 1 and a y-coordinate of 3. Okay? Similarly over here, if I tell you that f of 4 is equal to 0, that corresponds to an ordered pair with coordinates 4 and 0. Okay? And so if I go ahead and take a look at this question framed in that direction, it's saying is to write a linear function for which 1, 3, and 4, 0 live on that line. Okay? And these are exact questions that you guys have taken a look at in the past whenever you've done simple algebra questions. So I'm just going to reiterate my, my 2 points here, 1, 3, and 4, 0. And what we want, of course, is the slope, and we also want the y-intercept. And so remember that we have a slope formula for that. It's just the difference of the y's over the difference of the x's in the same order. Doesn't matter the order, we just need to keep it consistent in the numerator and denominator here. So I'm going to just go ahead and apply that. 0 minus 3 for my y's, and then 4 minus 1 for my x's here. If I were to do that, 0 minus 3, that makes negative 3. On the bottom, 4 minus 1, that makes positive 3. And if I do negative 3 divided by positive 3, I, of course, get negative 1 there. So my slope is going to be negative 1 on this line. And then if I want the entire equation of the linear function, I might just go ahead and use another tool that we've talked about in the past, which is point-slope form. So that would be y minus the y-coordinate is equal to m times x minus the x-coordinate. I would go ahead and plug in my slope, which we just calculated. That's negative 1. And then as far as my x-coordinate and my y-coordinate are concerned, I have two options to pick from. I can either pick the 1, 3, or I could pick the 4, 0. And in general, I always like to try to pick the point that has a coordinate of 0 in it, because when I plug that in, there's really no math to do, because 0 make things disappear, right? I'll go ahead and plug in my x-coordinate there, and then you'll notice on the left-hand side, y minus 0, that's just y. If I distribute it in that negative 1, I get negative x plus 4. Okay, and keep in mind that y corresponds to f of x, so if I wanted to write this using function notation, I could absolutely do that for my final answer. So f of x is equal to negative x plus 4. If you wanted to check this, you absolutely could. You just need to go ahead and take your function inputs and plug them into this function right here and make sure that you get the corresponding outputs. I'm not going to do that in this video because that would, try to save some time, but that's exactly the same type of question we've answered before, but now it's just in the context of function language here, okay? For this next example, same thing, write a linear function for which f of 3 is equal to 9 and f of negative 1 is equal to 11. So remember that this corresponds to an ordered pair, 3, 9, and this corresponds to an ordered pair, negative 1, 11. So it's the exact same problem. So let's just run through that really quick, right? So maybe even try to pause the video and see if you could take care of this one yourself, and then come back and see if our solutions match up here. So if I subtract my y's, again, I could do that in any order here. I might go ahead and pick 11 minus 9 to try to avoid dealing with a negative there, but that kind of makes the order that I have to subtract the x's in the bottom something where I have to do negative 1 minus 3. So it looks like dealing with a negative is unavoidable here. Okay, so in the top, 11 minus 9, that makes 2. On the bottom, negative 1 minus 3, that makes negative 4. And if we reduce that, of course, it's going to reduce to a negative 1/2. All right, now I'm going to go ahead and start to get the equation of my line here going. So that's going to be my point slope form, which I'll start with here. I'll go ahead and plug in my slope after that, which was negative 1/2 we just calculated. And then as far as picking a y-coordinate and an x-coordinate here from a point, just make sure to pick from the same one. I always try to avoid dealing with negatives whenever possible, so I might go ahead and deal with that. If you pick the other point, though, and did it, that wouldn't be a wrong answer. You just need to make sure that you do all the steps correctly here. So if I plug in those coordinates, 9 and 3, this would just be something that I have to go ahead and solve here. So on the right-hand side, distribute that negative 1/2 in. So negative 1/2 x plus 3/2, and that's equal to y minus 9. And then if I go ahead and add 9 to both sides here, then I would get y by itself. Y would be equal to, it looks like here that would be a 3/2 over 9. That would be a 21 over 2. So I could rewrite this as negative 1/2 x plus 21 over 2. Okay? Now, that is the linear equation, but we want to go ahead and rewrite this in function language. So instead of saying y here, I would go ahead and take that out and replace that with f of x is equal to negative 1/2 x plus 21 over 2. Okay, so that would be the linear function that passes through those 2 points. And again, very similar to a question that we solved in the past, but again, now we've just presented this question to you in the language of functions. Piecewise defined functions are also something pretty important to point out here. Keep in mind how these work is when you turn these machines on and start feeding these numbers, the first thing the machine is going to do is it's going to figure out which category your input is going to fall under and then do the corresponding formula to calculate the output. Okay, so in order to make this a little bit more clear today, I'm going to go ahead and use 2 different colors. So I'm going to go ahead and do this first one in purple, and I'll do this second one here in green and then we'll describe how this process works, right? So piecewise means, of course, if you feed this function something that is less than 0, another way to say that, of course, would be if you feed this function something that is negative, apparently what's going to do is it's going to take that input you gave it and add a 4, and that's your output. On the other hand, if it's positive or 0, so in other words, something that is non-negative, if you give this machine something non-negative, then apparently what it's going to do is it's going to change the sign of your input and then take away a 2. Okay, so that's what it's going to do for your function output there. What we need to do whenever we graph this is just be careful about those two regions that we pointed out, because we have all of the x's that are greater than or equal to 0. Those, of course, are all the x's that live in this region here. And then separately, we have the region of x's that are all less than 0, so all the negative ones. So that would be to the left of your origin point. Okay? It's going to be in these regions where you're going to need to plot your functions, but only in those regions. So, for example, in purple up here, so I'll go ahead and change my pen color to purple, we want to go ahead and plot the function x plus 4, okay? Or in other words, y equals x plus 4. We're only going to do that in my purple region here. So I might just go ahead and zoom in there on my purple region, ignoring the green for a second. If you have x plus 4, then that means that your m, your slope, is going to be equal to 1, or in other words, 1 over 1. That means for every 1 that you rise, you would have to run 1. And then your y-intercept, playing the role of b, is, of course, 4. So that is going to correspond to a point with coordinates 0, 4. Okay? Now, this is going to have to be something that is plotted strictly for x values that are less than 0, so not equal to 0 itself. So when you plot your region here in purple, we're going to need to put an open dot in purple on that value of 0, 4 that we need to plot first here. So if I come up here to 1, 2, 3, 4, I'm going to go ahead and put an open dot there, just to signify that that is a value that I approach but I don't equal. And then we would go ahead and use our slope formula to get the rest of the line. I'm not going to graph this in green territory because that is for a different function. I would continue to graph here and here and here, but again, if I follow that pattern in the reverse direction, I would have all of these points plotted in this direction here. So again, just kind of following that slope all the way through, that would be the equation that I would want to graph there in purple, okay? But then, of course, when I switch gears and I now have x values that are greater than or equal to 0, this is where we would begin to plot the other one, okay? And so if we take a look at the slope m for that, that is going to be a -1, so that's -1 over 1. That means for every 1 unit I fall, I run 1 to the right. And then playing the role of b in that green part would be -2, which means that I would start this process at a point with coordinates 0, -2, and then continue here. So if I am at 0, -2, this is where my x's can be greater than or equal to 0, so I am going to go ahead and have a solid dot here on that value. So if I come down here to -2, I would go ahead and simply plot that point. And then, of course, my slope is -1 over 1. So that means, of course, for every point that I fall, I have to run 1. So that would look, of course, a little bit like this if we were to plot it. Okay? Now, I would like you to go ahead and take some straight edges and make sure that you're lining it up here and drawing that picture of the graph. That would be what we would want to do. So let me go ahead and take my virtual straight edge here, and we'll just do the best we can, lining that up and striking my pen all the way through to create that portion of the graph. That looks pretty good to me. Make sure to include that arrowhead to signify that that reaches indefinitely in that direction. And then also the same thing for this other guy here. So take my ruler and now line this up to the other set of points that I drew here in green for my other region. And we would want to just simply go ahead and strike my pen all the way through on that as well. Okay? And so this is why we call them piecewise functions, is because depending on the descriptions that your machine is trying to match your input up against, it's going to create two different regions for your function whenever you try to graph that. So let's take a look at that one more time here, and then we'll call it a video. So we have this function formula right here. Again, I'm going to stick with the same two colors as before. So apparently all the inputs that are less than 1 strictly, those are going to be one of the regions that I need to graph here. So let's go ahead and quickly point that out over here on the graph. So starting at -1, I would want to go ahead and be everything less than that for my purple region here. And then switching colors here on the other region, all the x values that are greater than or equal to -1, I would go ahead and have all of these x values that live in this region here. So that is where my function is going to break apart. And before, when my function broke apart at the y-axis, it was really easy to tell where they break apart because we were able to see that y-axis as a separator. Less obvious here. So one of the things that I like to do is go through and do a little bit of a dashed line up and down. And the reason I do dash is because it's not really a part of my function that I would like to graph. So it's just an imaginary boundary point between these two different regions here at -1. Okay, so what do I need to plot? Well, it takes, if you take a look here, we need to graph this region up here where your x's are less than -1. If we switch that around and rewrite that, then that would be something that looks like y is equal to positive x minus 3, where the interpretation there, of course, would be that playing the role of your slope is 1, aka 1 over 1. So for every 1 that I rise, I run 1. And then playing the role of b there, of course, would be -3, and that, of course, corresponds to the point with the coordinates 0, -3. Okay? Now, if you take a look at the graph, we're going to plot my purple part, but you'll notice that where I usually start this process is at the y-intercept, and that is beyond the point where my purple part can reach. So what I might do here is I might just go ahead and visualize for myself real quick in a different color where that y-intercept would be, and then use that as a skeleton to create the rest of the line shape. Okay? So if I start this at -3 down here, I'm just going to do this in a different color, like say white. I would go ahead and start there and then create the rest of the picture of my graph. So that would be to rise 1 for every 1 that I run. Okay, so that would be something that looks like this. But keep in mind, I'm in that green region. The only reason I'm doing that is so I can kind of follow the pattern here and continue doing my line here, but in purple. Now, on that boundary line, this is the x values that are strictly less than -1, so that means I'm going to have an open dot here where I would need to put my point, and that, of course, would be right there if I'm just following the pattern of my line. And then here in my purple region, I can go ahead and start plotting some purple points, which I will actually go ahead and draw my line through. So these white points here, this was just so I can get a feel for what that function would look like. And then I'm going to go ahead and take my straight edge here and line this up, and then go ahead and create that portion of the graph just like that. Okay, so that's pretty straightforward. Now let's go ahead and move on to the green part here where we are going to be having x values that are greater than or equal to -1. And so for that process, we're going to be taking a look at this second function formula right here. So this is going to be -1/3 x plus 1. Okay, so if we take a look at that and interpret that, then that would, of course, be y is equal to -1/3 x plus 1. We're playing the role of m is, of course, -1 over 3. That would mean for every 1 that I fall, I run 3 to the right. And then for my playing the role of b, it would simply be +1, and that would, of course, correspond to a point with coordinates 0, 1. Okay. Now, it looks like in green, this is a region that contains my, my y-axis, so I am free to go ahead and start plotting at the y-intercept there like we're used to doing. Okay. So that is, of course, going to be at +1, which I'll go ahead and point out is right there, of course. And then we have a slope of -1 over 3. So that means for every 1 that I fall, I have to run 3. And so I would put my next point there, and then continuing to follow that pattern. That would be the straight line pattern that I would want to match up here. So I'm going to go ahead and take my straight edge, and I'm going to line it up against these points, and then we would see exactly where we would touch that boundary line. And so I might just go ahead while I have my straight edge pulled up here and make a little bit of a marker there so I know exactly where to put my, my solid dot, because it can be greater than or equal to -1 here, remember. And then might as well just go through, since I have my straight edge lined up, and go ahead and draw that portion of the graph there. I'll get rid of my, my straight edge and then go ahead and put a solid dot right there on that value to just signify that that's where that green portion starts. So when you graph piecewise functions, you do have to pay attention to those regions that you're splitting up your x-axis into, and then you're only graphing certain parts of these piecewise functions on these specific regions here. And that's it for this video. So I just wanted to kind of go through quickly your linears and your piecewise functions containing linear pieces. So if you guys have any questions whatsoever, please feel free to let me know. But that's all I have for this one. Thank you very much for your attention, and I will speak to you in the next one.